we will change gears a little bit because I'm not chemist, I'm not engineer, I'm ecosystem ecologist, so my view on all this is a little bit different. So yeah, we had quite a few talks which prepared ground for my talk, so I don't want to spend too much time on it. I'm coming from Ben Gurion University of the Negev in the Negev Desert, Bernstein Institute for Desert Research, and my institute has very long name on agriculture and biotechnology of arid lands. So we know that we need to recover nutrients from gray water. We know that we need to recover nutrients from sludge, and there are a few different types of application types of this recovered nutrients. One is direct aquaponics based on, for example, if you have growth of fish, you can aquaponic product after, or you can grow biomass and then apply biomass as fertilizer or soil amendment, or you can do some treatment and apply whatever out of this treatment as amendment of soil. This is all stuff which is known for engineers better than for me. So I don't know this very well. But this is, for example, hydrothermal carbonization, which is we're taking sludge, doing some voodoo, and becoming stabilized hydrochar, which is biochar, but hydrochar. And this sludge can be done, in our case, it was done from human sewage. So it's human sewage, not animal. And we have person who does it a lot in his lab, and we collaborate. So my point, what I came to talk to you about is about how we approach at least carbon sustainability, or at least climate sustainability. Sustainability is very word which everyone uses, so I will use it as well. Sustainability is not about it's how to sustain something for a longer time, right, for next generations. So I will speak about climate, because I measure greenhouse gases, so I speak about climate. A few years back, we put together a conceptual framework to study environmental impact of managed ecosystems. So when we have some agricultural ecosystems, so any managed ecosystem, we need to account for all anthropogenic inputs, for soil fluxes of greenhouse gases, for harvested biomass, because in agriculture we want to harvest biomass, and we need to account for soil. And if all this will be plus, means that we emitting CO2 to atmosphere, and if it will be minus, we sequestering CO2 into the ecosystem. And we will use, for this we will use CO2, because CO2 is acceptable money for carbon accounting. CO2 equivalents, for example, kilogram of nitrogen fertilizer production is about 6 kilograms of CO2 equivalents emission, and 1 kilogram of N2O is about 300 kilograms of CO2 warming potential. And this will be called global warming impact, and this is this chapter from book available online. Anyway, so now when we know introduction, where we work. I work in Israel. This is Israel, this is Nebraska, so a little bit smaller than Nebraska. We are relative to news about Israel, we're a very small country. And you can see it here. And our own university was studying from 70s, studying Be'er Sheva. This is Negev, the largest part of Israel. I live here in the middle of the Negev. And we have about 20,000 students in main campus, and we have another campus where I work here. And so first, I will show you a few examples of my approach to this problem of sustainability of application of all this stuff. First one will come from this point on map is Hatseva, where we have very nice R&D station, research and development station, where they do experiments for us. We just pay money and they do experiments, because I'm not agronomist either, right? I don't know agronomy or how to grow crops. So we did some, it was published years back by a PhD student, Thomas. So we have three different treatments. One is fertilizer, nitrogen fertilizer aquaponics. Aquaponics, we're growing cucumbers. Cucumbers grow well in aquaponics and it's good fruit, vegetable, I mean, to eat. So 600 kilograms per hectare of application of nitrogen, and it's FN is inorganic nitrogen. Then we're using only fish water, the same amount of a little bit less nitrogen per kilogram per hectare, and we growing cucumbers, and then we use fish water and adding ammonium. Why we adding ammonium? Because farmers like to add stuff to the water, even if it's not needed. They need to add fertilizer, so we did some kind of fertilization addition to irrigation, and it's all in flowing aquaponics. Now, first yield, because we want yield. Yield was same in all treatments, about 120 tons per hectare. Fresh weight, it's about 85% water. But we sell fresh weight of cucumbers. No one buys dry cucumbers, right? Only fresh cucumbers, so it's okay. And nitrogen efficiency about 40%, which is very good. 40% is maybe average nitrogen efficiency is about 25-30%. We have about 40 in gramen applied and gramen in plant, and this is a season of 2 months. So nitrogen allocation in this case, we because it's aquaponics, we can do nitrogen budget more or less. It's not total. We're still missing parts, but we're okay. So this is in inorganic fertilization with ammonium nitrate. We have large quantity of nitrogen going to fruit, some going to dissolved organic matter, and in fish tank water we have less, a little the same picture more or less, and same picture more or less in water with added nitrogen, ammonium. So means we have same amount of productivity. We have same amount of nitrogen partitioning. So what is different? Different is nitrous oxide emissions. We measure nitrous oxide emissions. I will show you machinery with use in one of the slides. I don't want to speak about methods, but we know how to measure very well, really, really well. So nitrous oxide emission, cumulative emission per milligram per meter square in very lowest in fish water, where you have only nitrate, a little bit higher, but still very, very low in fertilizer addition. But when we added fish water and ammonium together, we had huge amount of emissions, like 5 times, 6 times more. So it's all published, so you can read this pretty long paper. But what I want to stress that now we can calculate global warming impact of our production using reclaimed water, because it's aquaponics of fish water. So this is an organic nitrogen fertilizer cost of 600 kilograms of fertilization is 4,005 tons of CO2, because we have a lot of harbor bosch is very energy intensive. Nitrous oxide about 100 kilograms, and in total it will be what, over 5 tons of CO2 emission per hectare. And fish water, we have nitrous oxide. You see much less nitrous oxide. We don't pay for fertilizer CO2 payment, and it's very low amount of total global warming impact. And when we're adding a little bit of fertilizer of ammonia, so it was ammonia added from digester, not from outsource. So it's one kind of reuse of digested biomass, if I remember correct. And total we have, if we calculating CO2 emission per ton of fresh yield, we have about between 36 to 0 kilograms CO2, which is means that if we use hydroponic or aquaponic to produce vegetables is good. We can reuse water, and we can produce vegetables with free of price, of environmental price. And then, yeah, so if we are adding to this water treatment cost, because water treatment costs a lot of CO2, I'm speaking in CO2 money, right? Because so emission from water treatment is between 200 to 800 to about kilogram of CO2 per meter cube, and we used about 6,000 meter cube per hectare of water because we're producing fruits. And then if we're not treating it, we're saving another 5 tons of CO2 per hectare, which is great. The question is now what we do with this water. With aquaponic, it's one-way flow. We cannot return it. So basically, the idea was let's fertilize dates outside of greenhouse, and then we will enrich soil and all this stuff which is coming with water together. Okay, so second example of reuse of fertilizers. This was my master student a few years back. We had ammonia and biomass-based fertilization. What is biomass-based fertilization? We're taking gray water, but in our case it wasn't gray water, but we can do the gray water, and we're growing microalgae. Microalgae is a simple organism. They grow pretty well. They take up nitrogen and phosphorus from the water, and then we can take them out of water somehow. I'm not an engineer, and apply to the field. It was the same idea with biofuels once, but not working very well because very difficult to separate algae and water. But we did it still because I don't know, we got money for doing this, so we did it. This is laser I was using for NTOP and methane emissions. And speaking about equipment, it's $150,000 piece. And I use it in field all the time. Very good equipment. So we've been now in lab where he said how much equipment costs. So I remember how much mine cost. Okay, so we took 3 types of soils here. Okay, so it was done where I live. I live here. This cliff, this is here. And this is soil, how soil looks like. It's less soil, dryland soil, very high carbonate, about 50% carbonate, very low organic matter, about 0.2% organic matter, or even less. Very, it's not soil, basically. It's like kind of dust. This is how it looks like. And so we took 2 different applications. One is macroalgae growth with gray water, maybe this typo. But it's not real water because we cannot grow so much nitrogen. We apply 100 kilogram of nitrogen for wheat in Israel, and to apply 100 kilogram of nitrogen by biomass of algae is very difficult. And compared to urea, which is standard application for wheat in Israel. So it's how it looks like field side. We have had 3 soils, clay, loess, and sand. We did untreated algae. You see how it looks after the separation. We mixed it with sand because otherwise it's difficult to apply. And we hand applied and we planted wheat. This is a picture of, we did 2 years. 1 year wasn't so good, so this form not so good here. But we had wheat in desert. It's what we do in Israel. It's never irrigated. In our case, it was irrigated because we have about 80 millimeters of rain per year. And it was dry year, about 30 millimeters of rain, so 1 inch per year. So first yield was same in everywhere, which was surprising to me, and grain yield, right? Dry mass per meter square, except in clay soil, we had higher yield in urea fertilized soil. Good. Now, nitrogen content. Nitrogen content is very important for wheat because grain, nitrogen content is protein, right? It's protein of wheat. It's about 3.4. We multiply by 4 and to get nitrogen and protein content. And you can see that in sandy soil, we had no difference, but in loess and clay, we had less nitrogen and grain fertilized by algae. Means that it was not deficient nitrogen because they filled up grain without nitrogen. They had lack of available nitrogen. So while yield is the same, quality of yield is different, which is trade-off of application of biofertilizer. And emission of gases, N2O and NO, in this case we measured NOx. And you can see that different soils had very different response of emissions, and different gases have different emissions because we had about 80 milligram of nitrogen N2O and 300 milligram of NOx in sandy soil. And you can see how it's the same climate, different soils, different applications. So we removed climate, which is texture of soil, usually defined by climate. And if defined by climate, we cannot study texture without climate, if it makes sense. So here we can study texture effect without climate, which is very interesting for me as biogeochemist. And you see the different soils responded very differently. And yeah, and we also did microbial population analysis, and you can see that different soils have different population of microbes, but different treatments had no difference in microbial population, but very large difference in activity, because this is microbial activity, right? And this is microbial population. Microbial population, no change, activity changed a lot, which is I like very much, because I like this idea of microbes doing stuff, not genes. Genes don't do anything, microbes do, right? When they produce genes from genes by. And last application I want to show you is hydrochar. Hydrochar, this is a system we take into the field, methane, N2O, and CO2, and NOx, all in one place. A student working with the smallest experiment I done in my life, 75 liter of whatever it's garbage can. And you can see we applied hydrochar here, it's black, and we did no hydrochar in yellow, in sand, and we were growing lettuce, which is not real crop, but it's people still grow it, so it's okay. And we did fertigation, and we measured these gases from each random designed experiment, all this stuff, and it also was published just last week or so. So for treatments, one is sand with a little bit of less, but mostly sand fertilized by urea, 142 kilograms per hectare, which is what we do for lettuce. Sand amendment with hydrochar, 1% of hydrochar in top layer, and sand mixed with hydrochar and urea. Why urea again? And we did minimum fertilization, because without fertilization, plants die. So no fertilization, plants don't survive. If you don't feed them, they're dead, right? So like people. And this is how it will be shown in next slides. So here, this is hydrochar and fertilizer together. And here we do hydrochar and adding fertilizer, because in case hydrochar will be not enough to fertilize. The logic behind all this. So first, again, plant growth, and we do agriculture, we need plants. So when we added urea and hydrochar, we had with the best plant growth, all treatments. But when we added only urea or only hydrochar, we had the same plant growth. What does it mean? That plants can do well only with hydrochar addition, which is very, very good, right? It's excellent, because you don't need to add no urea, and you don't need to pay $1,000 per ton now. And this is through dry biomass, showing the same picture. In 40 days is how long we grow lettuce. Now, this is very, very slow chart, so I will go very slow, but this one was my last one. So first is cumulative emission of N2O in milligram nitrogen per meter square. And as you can see here, urea and hydrochar had much more emission of N2O than all others. And all others had very little emission of N2O. So this is trade-off of the best growth rate. We're getting the most lettuce, but we're also emitting most nitrous oxide, which is greenhouse gas. And blah, blah, blah. Now, cumulative NO emissions showing very similar pictures, but NO is not greenhouse gas. It's gas I like to work with. It's very important photochemical pollutant in lower atmosphere. And ammonia volatilization also happens because we have pH of 8.4, so we need to measure ammonia volatilization. And here, when we applied only urea and hydrochar, we had a lot of ammonia volatilized, which is expected because pH is high and ammonia volatilized, right? Yeah. Okay, now cumulative N2 emissions were driven by soil nitrogen intensity, means how much microbes saw nitrogen in soil over 40 days, more nitrous oxides they emitted. I like this measure because it's integral measure of nitrogen availability in soil for microbes. And here's ratio between N2O and NO emissions, which is dependent on organic carbon in soil, because N2O to NO ratio is about denitrification and nitrification. Denitrification is N2O producing and nitrification NO. And you can see that when we have more carbon in soil, we have more N2O relative to NO production. Again, also this amendment of hydrochar and urea together. And then we calculate the emission intensity, which is how much gram of nitrogen you're emitting to the atmosphere relatively to plant dry biomass, which is pretty standard to do. And we see here trade-off between application of hydrochar of good, application of good stuff, and emission of bad stuff. So this clear trade-off. It's what I wanted to talk to you today is about trade-offs. It cannot be one only positive. We don't have silver bullet. The silver bullet doesn't work, unfortunately. I would love to have silver bullet, but I cannot have one. So conclusions, you see already conclusion. First, aquaponics is good. Very good options for vegetable growth. In desert, the problem is electricity, because I haven't calculated, we calculated electricity use. Electricity use is pretty intensive, and electricity in Israel, at least, is very expensive. But you save on more water, which is also very expensive. So it's all depends on cost. Biomass-based fertilizers may reduce product quality. Nitrogen is protein, right? So product quality can be reduced while amount the same. So you can sell more wheat, but it's not going to be good one. No bread, only pita. And soil amendment of hydrobiochar, in our case, increased gaseous nitrogen loss. So I don't know, I haven't done any review, but I don't know how it's working in different places with hydrochar. Hydrochar is very speculative topic today in soil amendment stuff. Okay, this is thank you for you listening. It's not done for free. I get funded for everyone who gives me money. Basically, Ministry of Science, Science Foundation, BART, ICA, whatever. And my ibixes now live in our village, a lot of them. And then you can you're going out of office and they fight now because it's the season of fight. And you hear them very well. Okay, thank you.